In this video we will show how to calibrate a rock physics model. Earlier we have showed how to import, format and QC well logs. When you are going to go ahead and calibrate a rock physics model, it's a good idea to create a new project for that. So we do that. And then we go and specify where the data is going to be collected from, so that it's using the same data that we had prepared in the previous project. Then we need to go ahead and import the well logs. And one of the reasons for creating a new project is that we don't need to import all the well logs now. We just need to import those final QC'd well logs, and we can continue our work from there. So we have imported well A here, and we have a lot of models that we can select from in the rock physics model library here. For example, the modified differential effective medium model. You can go ahead and read the description or search for a description of it on the web. But we're going to proceed here with the patchy cement model. And what you can do is you can hover over items to get more description about the parameters. You can go in here and use the unit calculator to use other units than the standard entered units. So if you're familiar with using bar for the pressure, for example, you can do that. In a rock physics model there can be many parameters, and we try to divide this into more groups, let's say. So you had the environment page first, and here we are dealing with solids, and you can specify different properties for it, and you can also specify how the solids are going to be mixed. Looking at the description of the model, you can see more details about what the different mixing models are, for example. And you can access the description from this page here just by opening the save model, but just don't save it yet. And then we proceed to the next page where we deal with the fluid properties like salinity, gas gravity, oil reference density, and so on. And here in this case, for this well, I know these values from before, having checked some well reports or something like that. So I put in those values. On the previous page with the solids, I used the quartz properties for the solids, but I left the shale properties, I don't know. I will be calibrating those at a later stage. So I basically put in the values that I know from before, and I don't take too much notice of the values that I don't know at this stage. Finally, there are the effective porosity, volume fraction of shale and water saturation here. And again, don't pay too much attention to those. We are going to get them from the well log. And you can also get this overview of all the parameters. Then we proceed. We choose the well log and we specify the density, P-wave velocity, S-wave velocity. And from them we are going to derive other parameters. Then we are going to specify which properties from the well log are we going to use as input to the model. Here is the effective porosity, volume fraction of shale and water saturation. Then we reach this plotting page, you could say, and we have some predefined templates that we can use. And I'm just going to customize one of them to show you how you can do this. You can just edit it and then save it. You can see here now I can switch between them and I have my own templates. And I can use this to quickly plot the density, bulk modulus and shear modulus with different colors. So you can see here now on the plot here we have cross plot of data versus model and with different color codes. Now they didn't fit very well, so that's because we haven't calibrated the model yet. To do that, we go into the Calibrate and we specify some properties that we want to calibrate. For example, the critical porosity we give it an initial value, a minimum value, and a maximum value. So within that range, it's going to try and find the optimal parameter. Then we proceed with specifying the other properties, like max cementation, we are skipping the sand properties. Instead, we want to calibrate the shale properties. And we want to calibrate the friction factor. And then finally the patchy cementation fraction. And then we specify which properties we are going to evaluate for. We're going to evaluate the density, bulk modulus, and shear modulus. And we set some axis ranges. And we are going to plot while it is calibrating. We're saving the template and proceeding with the calibration. So what happens now is that it's testing out different combinations of these properties, changing them, trying to find the optimal fit, and we can see here the crossplot of density, bulk modulus, and shear modulus. And the data points are dancing as it's trying to find the optimal fit. There is a cost function up in the top that you can see how well it's performing. We want this cost function to be as low as possible. So skipping a little bit forward here, we see now that there is very little change in the cost function. And it's possible to not go all the way through with the calibration. You can stop it at an earlier time. To do that, you just hit the end calibration button. Now you can see here all the parameters that we tried to calibrate, their initial values, and the normalized root mean square deviation is that cost function. You can see the calibrated NRMSD, and we just update all the parameters here. What you want to do at this point is to save the model, so we're going to give it a little bit updated name here, adding calibrated, and saving this model specification to the library. Then we can easily access it at a later time. So you can edit the description also. Now we can go ahead and do the cross-plotting again, and this time it will give a better fit. We are plotting data versus model, and we can compare here with before the calibration, and we can see that we have achieved a better match between model and data values. This can of course be improved even more. Maybe in addition to calibrating the shale, you calibrate the sand properties, that it might not be clean quartz. You can also filter the data, let's say only including data with low volume fraction of shale. Having a high volume fraction of shale, it might actually be a different model that should be used. So you have different possibilities to improve the calibration in this way. Now what we see here is that we have saved the model, so we can access it from the model library, and we can go back and continue working with this at a later stage. See here the values are updated compared to the default values. A final word about the rock physics model library is that it does not contain forward model results as such. Instead, it contains recipes of the various rock physics models. The advantage of that is that you can customize models to your needs, and you can go back and review the specifications at a later time and even update them. And then you can use them to the type of forward modeling you like, using the default properties that you have specified, or overriding them like we did with the effective porosity, volume fraction of shale, and water saturation.